communication, by which I mean avoid moving data, the most expensive operation any of these new computers do. And I'll start by talking about direct linear algebra. I'm going to tell you about new lower bounds on the amount of communication that any solution of this, all the world's standard linear algebra problems have to do. Solving linear systems, least squares, eigenvalue problems, SVD, many, many more. And then I will give you new algorithms that attain these lower bounds. None of them are in standard libraries. The standard libraries all do asymptotically more communication than is necessary, and we have large speedups for everything. And then I'll do all the same thing for iterative linear algebra, which is, conjugate gradient Krylov subspace methods. So let me say a few more words about what communication is. Algorithms have two costs, floating point arithmetic, and then communication. And so I'm going to talk both about the sequential case, moving data between levels of a memory hierarchy, cache and DRAM, and many levels of cache, and between processors over a network in the parallel case. So I'm going to have a very, very simple model in which I'm going to state these lower bounds. There are three terms: flop times the time per flop, the words moved divided by the bandwidth, and the number of messages times the latency. And all of those coefficients are growing apart exponentially over time. So the time per flop is very, very small, and it's much less than the reciprocal bandwidth, and it's much less than the latency. And all the technological trends, Moore's law and so forth, says they're growing apart exponentially. So this is a little bit of an old data from an old NRC report I helped write. The time per flop, Moore's law, is growing. It's improving 59% a year. The bandwidth is also improving, but at half the rate. The latency is improving even more slowly. And subsequent data has already validated this. It's still going on. So even if your algorithm is not communication bound today, it might be next year or the year after that. And so that means that our goal now is to reorganize all of linear algebra to avoid communication. I want to do provably as little data movement as possible between all possible levels in memory hierarchy, L1, cache, and L2, and so on and so forth. Now there's another word people use in this business called hiding communication. That just means overlapping communication and computation. That's a good idea, but that can give you at most a speed up of a factor of 2. I'm going to get arbitrary speedups by not communicating in the first place.
Is your latency just between to disk or memory?
Between any two objects that you want. So my model is to move n words costs the latency alpha plus n times beta, the reciprocal bandwidth. So that is my model that I'm going to try to minimize. So, and you don't have to take my word for it that this is a good idea. You can take somebody at a much higher pay grade than mine. So President Obama, in the 2012 budget request to Congress, had a couple pages of 2010 highlights. And one of them was the Trillinos project at Sandia National Lab, which is Mike Caru's project. It says, on modern computer architectures, communication takes much, much longer than performance of floating than moving data around. And so the important thing is to minimize communication between processors by reformulating the communication patterns. And that was referring to one of the algorithms I'll be telling you about today.
Who wrote that?
Who wrote this particular DOE report? Somebody in the DOE, some high-level program manager. I don't really know. There are a couple of pages, it's a multi-hundred-page budget request, and there are a couple of pages of highlights from 2010. So, and I'm lucky to find it. I didn't notice it. Somebody else noticed it. So let me tell you about the history of this. So prior work on matrix multiply, which is the most studied algorithm. Surprisingly, we'll say something new about it by the end of the talk. I want to talk about the n-cubed algorithm for multiplying two matrices. And it's been known for many years that if your matrix fits in DRAM, it's very large, it doesn't fit in your small cache of size m, then a lower bound, no matter how you organize your n-cubed multiplications to do matrix multiply, is you have to move n cubed divided by the square root of the cache size data between slow memory and fast memory. And that was proved by Hong and Kun back in 1981. And we've known how to attain that for many years. It's in all the standard BLAS libraries, blocked algorithms and cache oblivious algorithms attain it. That lower bound was improved, or let's say it was extended to the parallel case in a nice paper in 2004 by Aroni, Tiskin, and Toledo. So assume my matrix is spread out over p processors, each one gets an equal share of it. Then a lower bound on the number of words you have to move between some pair of processors is n squared divided by the square root of p. And that's well known to be attained by Candon's algorithm. So what's new? This is a lower bound for all of direct linear algebra. So let me let m be the fast memory size. So whether you're a cache or a local processor and it's your local memory, let's call that m. Then the number of words you have to move to do anything, I'll show you what anything is the number of flops per processor that processor performs divided by the square root of the cache size. This applies to any algorithm that smells like three nested loops. We have a very careful mathematical definition of what smells like three nested loops is, but for this talk, your intuition is perfectly good enough. That turns into a simple lower bound of the number of messages. What's the largest message you can send if your memory is of size capital M? It's the number of words divided by capital M. So all I do is I take the first bound and divide it by M. So, and to apply that in parallel, I have to assume there's some load balance, right? Everybody's doing, one piece of the flops, whereas one piece of the data. Otherwise, I could put all the data on one parallel processor and not communicate at all. So just to avoid that little silly case. So what do these apply to? So the proof uses beautiful geometry from Loomis and Whitney from the 1940s, and I'll prove it to you offline. It has to do with modeling computation by using Euclidean geometry. It's an interesting idea, and later, if I have time. Yes. What it applies to, and what's new, I think, is it applies not just to matrix multiply. It applies to LU, QR, the eigenvalue problem, the singular value decomposition, tensor contractions, whole programs, which are compositions of these things, no matter how the individual operations are interleaved. It applies in both the dense and the sparse case. You don't have to do n-cubed work. It's, if you are doing a sparse matrix, you do some number of flops. It depends on the sparsity structure. That's what goes in the numerator. It applies to sequential and parallel algorithms, and it applies to some graph theoretic algorithms too, like Floyd-Warshall, which is kind of like doing matrix multiply, except instead of doing multiplies and adds, you're doing maxes and sums. Excuse me? The next slide. So do conventional dense algorithms as implemented in all the standard libraries, which I'm also partially responsible for, attain these bounds? And the answer is no. They're all asymptotically slower. So what we've done systematically over the last couple of years is discover new algorithms for all of linear algebra which do attain these lower bounds, at least in the dense case. So we have new algorithms which do attain all these lower bounds. And I can't tell you about all of them. I'll tell you about one. And we've only done a few sparse ones so far, and it's kind of funny. You'd think matrix multiply was the easiest thing to talk about, but in the sparse case, we only know how to do Koleski on sparse matrices with good separators, and then we know how to attain the lower bound. So there's still lots of open problems in the sparse case. So let me give you the simplest example, one which we've implemented in the most wide number of architectures, which is, we call it tall, skinny QR, which is the QR decomposition of a tall, skinny matrix. So let me assume, just for simplicity, my matrix W is spread out over 4 processors. Each processor owns a quarter of the rows. Each processor with no communication at all does a local QR decomposition of what it owns locally. So processor 0 owns W0, computes its QR decomposition. Then I notice what I've implicitly computed is the product of that matrix as a product of this block diagonal orthogonal matrix in this stack of 4 triangles. Okay, so that's the first step. Then I take that stack of 4 triangles, and I take the top half of them, and I again do its local QR decomposition. This requires these 2 processors to communicate. And so now I notice that's another implicit orthogonal times stack of triangles. And then I take the last 2, and I do its QR decomposition. And so what I have done is I've implicitly factored my original matrix as the product of those 3 red orthogonal matrices, which is then orthogonal, and the triangle at the end. So that is a nice, simple MapReduce, if you like, to do QR decomposition. And so let me just draw the picture, because it really is just a reduction operation, where the reduction is take 2 triangles and do a QR decomposition, and that's sort of the algorithm that works. It minimizes communication. If you remember, it's a factorization of matrix into orthogonal times upper triangular. And we teach undergrads, it's called Gram-Schmidt, but that's a terrible algorithm, but it's the same output as a Gram-Schmidt factor. And this is like the way you do least squares problems or do data fitting. It's like the kernel of all that stuff. So how do you attain the lower bound in the sequential case? I'm just going to use a different tree. It's the same idea. I bring W0. Suppose I can fit only a quarter of the data into cache. I bring in the top quarter of the matrix. I do its QR decomposition. Then I bring in the next quarter of the data, and I stack those 2 matrices on top of one another, and I do that QR decomposition, and eventually I get the whole thing. What if I have like a dual core machine with a cache? I might use that decomposition. And what if I have, a multi-core, multi-socket, multi-rack, multi-site out-of-core machine? Well, a real computer, in other words. Then I'm just going to have some other kind of shape reduction tree, and I'm going to choose the shape of that reduction tree dynamically to minimize the communication for the whole platform. So here's some speed up numbers just to give some illustrations. 8x over the previous best implementation on an Intel Cloverton, that's a multi-core machine. 6.7x on a Pentium 3 cluster, 4x on a Blue Gene L, 13x on a Fermi Tesla compared to NVIDIA's best previous implementation, 4x on 4 computers in 4 French cities. You can imagine how long it takes to move data between French cities. And so there we get union rules and all that. So there are all these. So anyway, so that minimizes communication. We have it up and running in the cloud. You can see it's a natural kind of cloud application, but I don't have any idea what the performance data means yet, so I'm not going to say anything about that. And we even get a larger speed up. We get infinite speed up in the sequential case. This is a little artificial. This is comparing the version I just told you with LAPACK using virtual memory for something that doesn't fit in cache. LAPACK never finished, so it thrashed. But the new algorithm finished only twice as slow as though there were infinite real memory. So it sort of made the disk only slowed you down by a factor of 2. So let me sort of give now, and as I say, we have new algorithms for everything. I just told you about one of them. Let me tell you what sort of a summary of all of the parallel algorithms. And so what I'm going to do in one slide is tell you about the status of matrix multiply, Cholesky, LU decomposition, QR decomposition, the symmetric eigenvalue problem and the singular value decomposition, and the non-symmetric eigenproblem. And what I'm going to tell you is how close our new algorithms get to attaining the lower bounds, and compare that to the standard implementation of the ScalaPack library. So here are the lower bounds. You have to move at least n squared divided by the square root of p words between processors, and you have to send at least the square root of p messages. So let's look at the bandwidth first. And so for matrix multiply, we're within a factor of 1 of the lower bound, so we hit the lower bound. All these other algorithms are within a factor of log p, and in the complexity business, a factor of log p, you declare victory. Except for the non-symmetric eigenvalue problem, the new algorithm does hit the lower bound within a factor of log p, and it's much, much better than the old one. So here the improvement isn't so great. The big improvement is in the number of messages. And here, all the new algorithms are within a factor of log p, and the old ones are factors of n bigger, or square root of n. I mean, that's really, really big. So that is, the payoff here, and I'll show you some speed-ups in a moment. We go from being factors of n away from the lower bound, and n is arbitrarily large, to being within log p. So here is some predicted speed-ups for our new LU decomposition routine compared to the ScalaPack one on a future exascale machine. This is based on some parameters, a study of the Department of Energy, what this exascale machine will look like. And so the horizontal axis is log p up to 2 to the 20th processors. Each of those is a 1,000 core machine. And the vertical axis is the amount of memory up to, I filled up the entire memory down to, it's a really, really tiny matrix. Logs, so it's the log of n squared over p. And it's color-coded by speedup. And the speedup goes up to a factor of 29, predicted. Now, up here, there's no speedup at all. This is the realm of the LinPack benchmark. The n-cubed flops totally dominate the n-squared communication. There's no benefit. It's when you have medium-sized problems that you want to use lots and lots of processors, then communication begins to dominate, and it wins. Now, let me go back to this slide and ask, can we do better? So it looks like we can't do a whole lot better because we're within a factor of log p of the lower bound. But where did that lower bound come from? There's an assumption in that lower bound, which is that we only are allowed to use n squared over p data per processor. That's just an assumption, that I'm only allowed to have one copy of my data. Why should I assume that? So let me try to beat that lower bound arbitrarily. And so what I'm going to do is observe that the lower bound that we proved is actually the number of flops done by each processor, n cubed over p, divided by the square root of the local memory size. And if you only assume one copy of the data, the local memory size is n squared over p. So the question is, can I use more memory to communicate less? And so here's a prior example. It's a 3D matrix multiply algorithm. It's been around for a long time. And it uses, I call it 3D because it works on a processor grid that's cube root of p by cube root of p by cube root of p. And it has p to the 1/3 redundant copies of the two matrices. And that reduces the communication volume by a factor of p to the 1/6, that hits the lower bound, and it reduces the number of messages down to a factor of log p, which is also minimal. So, but this algorithm only works for matrix multiply, and it assumes you have a lot of extra memory. I have to have redundant copies of p to the 1/3. Well, it turns out that what we figured out how to do was extend this to as much extra memory as you might have available. So if you have room for C copies, 2 copies, 3 copies, 4 copies, I can take advantage of that, run the data on a grid that looks like this, and reduce the communication volume by the maximum possible, by a factor of the square root of C. And so we have some data. It runs, we eliminate 92% of the computation, of the communication, on a 64,000 processor IBM BGP, and we get speed-ups of 2.6 on medium-sized matrices running LU and matrix multiply. And this just won the best paper prize at Europar 11. So it all extends to Strawson. So let me sort of tell you what the story is there. So this is the lower bound. Let's just talk matrix multiply. We know Strawson takes n to the omega, n to the log base 2 of 7 multiplications. And so how much data do you have to move to do Strawson's method? Let me compare the Strawson lower bound with our old lower bound. If I log base 2 of 8, that's n cubed, right? So this is the n cubed algorithm. And if this simplifies to n cubed over the square root of m, this is what the Strawson lower bound looks like. All I have to do is change 8 to 7, and it all works. Now, the proof doesn't work. The proof is completely different. It uses all this fancy spectral graph theory. And this just won a best paper prize at SPA, so I'll let you read that later. So, and it also extends to any Strawson-like algorithm, Coppersmith-Winograd, all that kind of stuff. All you have to do, again, with the spectral graph theory, is change that exponent from whatever the exponent is for Strawson to the other exponent. That's a sequential case. And for the parallel case, it all sort of extends over naturally. The lower bound applies to the parallel case, in where I am only allowing myself one copy of the data, n squared over p per processor. It all works. And it also lets me have the multiple copies. So I can have C copies of the data, and it also extends to that. And it's attainable, partially. So we know how to reach this lower bound. I mean, the classical algorithm Strawson that we teach all sophomores, right, that works. It attains the lower bound. But we can also use it to attain the lower bound for LU, QR, eigenvalue problems, SVD. We've reformulated all of those to use Strawson or whatever as a black box, and they also attain the lower bound. But for the parallel case, we've only attained the lower bound for matrix multiplication. So let me summarize the first half of the talk. We have new lower bounds, optimal algorithms, big speed ups in theory and practice. There's lots of other things to talk about in open problems. I didn't say how we had to do LU. You can't do partial pivoting anymore. There's a different kind of pivoting that we had to prove was stable that does work. So we had to sort of reinvent new algorithms, new ways to do pivoting for LU, for QR, for all those kinds of things. All the lower bounds apply to heterogeneous architectures, so that all the processors don't have to be the same. Since the bounds work processor by processor, you can still sort of get global lower bounds. And we have still very few algorithms that attain them, but we're working on it. We only have a few sparse algorithms. And so actually, how do we build this software, which is sort of work in progress? The model that we use, latency and bandwidth, is too simple to capture all the difficulty and complications of real machines. So what we use it for is to define a tuning space, an auto-tuning space. Here's the class of algorithms. We don't know what the block sizes are, but we define those, and then we use auto-tuning search to try to find the best implementations in that space. So are there any questions before I do it all again for iterative linear algebra? Yes? So all the algorithms are equally stable as before. That was certainly our goal. And in the case of LU, as I said, we had to invent a new pivoting scheme called tournament pivoting, which I have more backup slides on. So it's not partial pivoting, but we proved that it has similar numerical stability properties.
Even for the eigenvalue?
In the eigenvalue problem, just as orthogonal transformations, it's stable for the same reason. Okay. So let me say a little bit more briefly about iterative linear algebra. So what I'm talking about are methods for solving AX equal B or AX equal lambda X. And all of these algorithms, what they have in common is they have a loop. In the inner loop, you do a sparse matrix vector multiply. You multiply your big sparse matrix by a vector. You generate a growing subspace. It's called a Krylov subspace. And then in that space, you pick the best answer. And this covers a big range of algorithms, conjugate gradients, GMRes, Lanczos, Arnoldi, whatever. So our goal is to minimize communication. And I'm going to assume my matrices are well partitioned. They have good separators for all this to work. And so in the serial case, what's the usual thing? I have a loop. I take k steps through the loop. I have to do k sparse matrix vector multiplies. My matrix is so large, I have to move it from slow memory to fast memory k times. The new algorithm moves it once. I can take k steps for the price of 1. And in the parallel case, p processors, what's the conventional algorithm going to do? The inner loop does a sparse matrix vector multiply. Every one requires communication with the neighbors to get some matrix entries. So the cost grows like k times log p for the reductions. The new cost is just independent of k, independent of the number of steps. It's log p, and that is also minimal. And so again, we get lots of speed up, both modeled and measured. And the price is some redundant computation. And I'll show you that sort of shows up in my assumption about the matrix being well partitioned. And also, stability is trickier. We have ways of doing it, but it's making these algorithms numerically stable is trickier. So let me just show you a cartoon for the world's simplest sparse matrix, a tridiagonal matrix, 32 by 32. I can draw every dependency and show you how it works. So here's my vector. Each dot represents a vector entry, x1 through x32. I want to compute a times x, so each of these is an entry of a times x. a squared and a cubed, and I want to do that with as little communication as possible. So here's the dependencies, right? Since it's tridiagonal, every entry of a vector a times x depends on 3 entries of the vector I'm multiplying. So you can imagine that those lines being repeated everywhere, and to keep the picture from getting too busy, I'm just going to draw it as a triangle. So the guy at the top of the triangle depends on the 3 guys at the base. And that, again, repeats itself everywhere. So that entry of a cubed x depends on those 3 entries of a squared x. And if I continue the dependency graph down, that's what it grows to. So that entry of a cubed x depends on all these entries of x. And if I want to compute more entries of a cubed x, right, it's the same idea. So now, what is the sequential algorithm? What I'd like to do is compute all the black dots and read the matrix A once. So in step 1, I'm going to read in these rows of A, these entries of X. I have everything I need to compute everything in the blue trapezoid. Then I will save just the border, and I'll compute the next trapezoid, and then the next trapezoid, and then, trapezoid, parallelogram, and then the next one. And so what I've managed to do is read in each entry of A exactly once, and write out each component of A exactly once. In the parallel case, it's almost the same. So suppose I have 4 parallel processors. Each one is going to be responsible for computing a quarter of the black dots. And so here's processor 2. It wants to compute everything between, in it that it owns. So what other data does it need? It needs to get one message from its neighbors to get these 3 entries of X from that processor, those 3 entries of X from that processor. And then it has everything it needs to compute everything in that trapezoid. And now, what do all 4 processors do? There's some redundant work, right? Because these trapezoids overlap. And so the triangles are done repeatedly. So it's easy to see all of this in a tridiagonal matrix case, but it works for arbitrary sparse matrices, and it's just a matter of doing some breadth-first searches, and it's the same idea. And assuming that the matrix is well partitioned, then I don't get too much redundant work. So how do I now take that as a kernel and rewrite all of these linear algebra algorithms? Let me take the simplest one, which is generalized minimum residuals, GMRes. Here's the standard algorithm. I want to take k steps. I do a sparse matrix vector multiply. I run modified Gram-Schmidt to make the vector I get orthogonal to all the ones previously. Then I do some updating of some little Hessenberg matrices. And at the end, I solve a least squares problem to get my solution. What's the new algorithm look like? I compute a different basis of the same Krylov subspace with one call to that kernel that I did before. I get a matrix W. I call that tall, skinny QR routine that I told you about to compute its QR decomposition. And then I have to reformulate the math in the rest of the algorithm. So all the algebra changes, but I can still get the same solution for the same least squares problem, just represented differently. And so, in the sequential case, the number of words that I've had to move is decreased by a factor of k. And in the parallel case, the number of messages is also decreased by a factor of k. And so, if you are looking at this carefully, you should say, oops, you have a bug. It's not a bug in exact arithmetic. It's a bug in floating point arithmetic. Because what is this kernel doing? It's computing. It's using the power method. It's all of these vectors are getting more and more nearly parallel to one another, and so I'm losing numerical stability. Well, let me run an experiment just to see what happens. And so here's a convergence plot where I've taken that algorithm, and the horizontal axis is the iteration number, the vertical axis is the log of the residual, the black line is the usual algorithm, it converges, and the blue one is the algorithm I just showed you, and it does completely numerically unstable. And that's because I've used this, what I'll call monomial basis, and it's just totally numerically unstable. But I don't have to use that basis. I can use different polynomials. So I get the same Krylov subspace. All I have to use is a different basis. And if I choose them cleverly, and we have various ways to do that, then I get convergence the way I wanted it to. So that's finally the algorithm that we need to use. And so here's some speed-up examples from a paper from Supercomputing 09. This was done on an 8-core Intel Cloverton. So we had to use both the sequential optimizations to minimize off-chip memory traffic and the parallel optimizations to minimize inter-core traffic. And the speed-ups, range from 1.7 up to 4.3, and it's kind of color-coded by whether the dense part sped up a lot. So going from purple, let me get this right, going from purple to yellow, that's the speed up of the dense linear algebra, and going from blue to red is the speed up of the sparse linear algebra. So they were both important to get right, to get the speed ups. And when we first did this, it was a disaster. What we did was we had one student who was tuning all the sparse linear algebra, another student who was tuning all the dense linear algebra. We put it together, and we had a big slowdown. And we realized that was because when you optimize these 2 kernels independently, they fight one another over the cache. And so what we had to do is co-tune. We had to tune the 2 kernels in situ so that they didn't fight one another, and then we got these speedups. So that means we can no longer build a sparse linear algebra library and have it tuned. like a sparse matrix vector library and a dense linear algebra library, and put them together and hope for the best, you have to tune it all together. So here's some more predicted speedups in this future exascale machine for this stuff, factors of up to 8.5 for a simple 2D Poisson model problem. So to summarize the second half of the talk, new lower bounds, optimal algorithms, big speedups in theory and practice. We've done lots of other algorithms too. GMRes is what I showed you, conjugate gradients, BiCG stab, Arnoldi, Lanczos. There's an alphabet soup of these different things. Other Krylov subspace methods could be done well. We still have to figure out how to recognize these stable variants more easily. Which polynomial basis do we want to pick? If you're in this business, you know you like to use preconditioning, not just these methods out of the box. And we've identified which preconditioners will let us minimize communication, but that's still work in progress. And again, auto-tuning is important. So for further information, all the papers on this stuff are at this webpage. I taught a 1-week short course on this last summer, and so you can sort of download all the slides for that. And if you Google parallel computing course, the top 2 lists are our courses, and we teach this material there. And the National Science Board is about to approve a proposal where we've promised to make all this course material for parallel computing in general, not just this, available nationwide with video and so forth. So this is joint work with an awful lot of people and with an awful lot of supporters. I'm not pretending I did all this myself. It's meant to be an overview. And so thank you to all of the supporters, including the National Science Foundation. And I know Microsoft is in the audience, and probably Intel, and probably a few other people. And we're hiring. So if you have a student or a postdoc who wants to join us, we have lots of work left to do. And so to summarize, it's time to redesign everything, all linear algebra algorithms and software, and eventually all of applied mathematics. Now what do I mean by that? I actually have a definition there. And so I'm going to base, I'm almost done. So this is an observation that was made by my colleague Phil Colella at LBL. And he observed, if you look at all the high-performance computing applications in the Department of Energy, there are only 7 kernels. They're all built out of what he called 7 dwarfs. And if it were possible to make this list, short list, of computations scalable and composable, and easy to put together, then you could sort of solve all the high-performance computing problems. So we've done a couple of those now, dense linear algebra and sparse linear algebra. And other people have worked very hard on spectral methods, obviously, the spiral and projects and FFTW. This is applied mathematics. So motivated by that, we asked ourselves, well, what about all the other applications in the world, not just high-performance computing? So we started a research group at Berkeley, and we looked not just at high-performance computing, we looked at CAD, machine learning, games, databases, spec benchmarks, and we did the same thing that Phil did. We took them apart and we asked, what kernels could we build them all out, and just sort of put them all together. And there were only 6 more. And here they all are: finite state machines, combinational logic or circuits, graph algorithms, backtrack, branch and bound search, graphical models. Michael Jordan wanted that one. And yeah, so they're all in there. And so in this heat chart says which one is important in which application. And so this is sort of our point of view that sort of underlies our educational material too that the NSF is adopting. The way we teach people is to say, these are the patterns that you should recognize in your problem that you want to solve, and then look to see if they are previously well-solved problems. And then we based a big lab on this, and we have lots of people working on it. And so the answer, how do we do this? You don't communicate. Thank you.
You're busy explaining how we don't want to communicate, and MapReduce is busy explaining how, well, we'll hide all that communication inside of a primitive so that it's easy for us to program.
Right.
I'm not sure about the relative sizes of problems that are being solved in numerical supercomputing versus what Google is trying to do.
Right. So and Google has some of the biggest matrices in the world.
More generally, I'm not sure about what is the tension or relationship between these two different approaches. Right?
Let me go back to one.
Should they just go use MapReduce to solve?
No, not at all. So we have, here it is. So cloud, early result. We have tried to implement this using MapReduce, and I think it might be adequate for this one algorithm, but we need to save state and be able to reapply it. And the trouble with saving state in the MapReduce world is it goes off to disk. It sort of maximizes communication. We want to leave that in memory. And so there's another lab at Berkeley that sort of works on cloud computing infrastructure. They have this system called Mesos, which is now being adopted by a few other sites, where you're allowed to leave state in memory and then come back and apply previous state to it. So it's becoming a more general programming model. It's not general enough. It may be good enough for this particular one. So, but we're collaborating with people who work in the cloud computing environment to build better infrastructure.
So, you know, connected to the previous talk, so there seems to be this trend of new architecture. It generates a whole bunch of new algorithms
Right.
that are re-implementing all the old.
That's why we got tired of it and decided to prove lower bounds that work for any architecture, and then find algorithms that will attain them. You know, in a certain big space, which still requires auto tuning to find the best implementation.
Right, and so the questions really, and the one you're partly answering, is kind of what kinds of problems are appropriate for which kinds of architectures, and what kinds of architectures are appropriate for which kinds of problems.
Right.
So how general can we go with this? And you
So
were answering it with the educational side there too.
So one of the directions we're moving to try to answer that question is extending all this to heterogeneous platforms, because when we talk to our industrial sponsors, they make it clear that the future is going to be totally heterogeneous, whether it's on one chip, you know, or a CPU with an attached GPU. So a lot of our work is sort of asking ourselves which of these architectures make sense for any of these. And so for this particular one, I have more backup slides. Depending on the dimensions of your matrix, you may want to, and suppose you have a CPU and a GPU, you may want to only use the CPU, only use the GPU, or use both. There's sort of boundary lines in the space of dimensions where you make different decisions. And so that's sort of the technical answer that we're sort of coming up with right now. Yes?
One quick question. There are a bunch of results on, say, approximate algorithms in the community for some of those problems. Randomized approximate
So let me speak to that. So, because I've certainly talked to people like Joel Trop and Vladimir Rocklin about this. So their approach would be to take a random orthogonal matrix generated by one of many ways, multiply your matrix times this small random orthogonal matrix, and then hope for the best that the product contains a lot of the information that you want. And you could say that if they pick all the dimensions right, they'd only have to access their matrix once. Our goal here is also only to access the matrix once. So what I would say is that as long as the number of columns of your matrix is less than the square root of your cache size, we can get the right answer accessing the matrix once. So above that threshold, so there's the threshold, then they would be able to access it once. And so I don't have a whiteboard here, but so what is it? How many times do we have to access the matrix to get the right answer by the usual definition? It's the number of columns divided by the square root of the cache size. So if you have twice as many columns as the square root of the cache size, we have to access it twice, right? So you can do this trade-off.
I guess the question goes to saying, one of the approaches is to say, how do you take a large matrix and make it small enough? And then,
Right.
you know, for example, less than the square root of the column size.
Right.
And then you can apply this one.
Right,
You
right.
can do it here as well. Those approaches potentially generalizing your model as well.
So what we could also say is how long would it take them to implement their multiplication by a random sparse matrix? That sort of fits in our scheme of things too. So it all kind of fits together. Yeah.
Okay, one last question, Richard.
Well, I have a couple of questions. How are you doing the scheduling? Is it a centralized scheduling or is it works?
So the lower bounds model doesn't care. It's sort of oblivious to that. The particular implementations have to make decisions about that. So we have a lot of joint work with other folks like Jack Dungara, for example, who's using DAG scheduling in order to schedule some of these algorithms. For other ones, when we write, so that would be a multi-core implementation. For the distributed memory MPI implementations, you know, we try to use all of the tricks in the LinPack benchmark as usual to have, you know, to do as much communication overlap as well as these tricks here. So all of the things that people have done in the past to optimize are still useful here. So, and it's a big design space, and you know, our lower bounds don't tell you which of those particular secondary optimizations are the right ones to use. We're still exploring that.